Algebra skills review number 4, simplifying radicals. I will be able to simplify radicals and rationalize the denominator. In this lesson, when we talk about radicals, we're going to be referring to the square root. So for instance, the square root of 4 is 2. Knowing our perfect squares will be important for this lesson. Perfect squares can be found by multiplying a number by itself. For example, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, and so on. The perfect squares are 4, 9, and 16. And what that means is if I were to create a square, 4 blocks would make a square. 9 blocks would make a square. And a square being that each side is exactly the same length. Square roots and simplifying radicals. A radical expression is an expression that has a square root. A radical expression could also be cubed roots or fourth roots and so on, but we're going to talk about square roots today. The expression is in simplest form, and the following have been met. No radicals have perfect square factors other than 1. So a factor are two numbers that are multiplied together. So for instance, the factors of 6 would be 1 and 6 and 2 and 3. None of those numbers are a perfect square other than 1, and that's not going to help us today. No radicals contain fractions. You cannot have something like this. And no radicals appear in the denominator of the fraction. You couldn't have something like this. The product property is that factors can be moved into their own radical symbols. So the square root of 3 times 7, which is the square root of 21, the factors of 21 can be their own radical symbols. The square root of 3 times the square root of 7. Things inside radicals can be multiplied together. So the 3 and the 7 can be multiplied together to get 21. But you can't, if there's something on the outside, you can't multiply that. You can't cross over the radical symbol to multiply it inside. The distributive property does not work with radical symbols. The quotient property. Same thing as the product property, but with division. That if you have a division or a fraction inside inside the radical, you can separate it into two pieces, the square root of 12 and the square root of, divided by the square root of 5. So simplifying radicals. There's lots of different ways to do this. We could do a factor tree, but as we start to get up into higher numbers, factor trees become quite difficult. So we're going to look for factors that are perfect squares. So if we think about the factors of 50, we have 1 and 50, 2 and 25, 3 doesn't go into 50, 4 doesn't go into 50, 5 and 10, and then we come back around. So these are factor pairs. So we want to look at the factor pair that has a factor where one of them is a perfect square. So 2 and 25 is a factor pair because 25 is a perfect square. So we can look at this as 25 times 2. And because of the product property, we can separate that. Square root of 25 times the square root of 2. And since 25 is a perfect square, when we take the square root of a perfect square, we get its factor. The square root of 25 is 5. And the square root of 2, 2 is not a perfect square, so it stays as the square root of 2. You could double check yourself to see if the square root of 50 and if the square root of 50 is equal to 5 times the square root of 2 on your calculator in decimal form. But simplifying radicals, that is the final answer. We don't have any factors inside the radical that are perfect squares. We don't have any fractions inside the radical symbol, and we don't have any radicals in the denominator. The next problem, the square root of 8 times the square root of 8 times 2 times the square root of 4 is our next problem. And we can look at this as two different problems. This 2, let's put it all the way out on the outside. So we rewrite this to say 2 times the square root of 8 times the square root of 4. Things inside radicals can be multiplied together, and things outside radicals can be multiplied together. That 2 is the coefficient. The radicals kind of work like a variable, where the coefficient goes on the front side. But before we multiply things inside a radical together, slow yourself down and ask yourself, are either number inside the radical symbol a perfect square? 8 has factors that are perfect squares, but the square root of 4 is a perfect square. So we have the 2 on the outside, and then we have the square root of 4. The square root of 4 is 2. So this red 2 comes from the square root of 4. And we still have this times the square root of 8. So we can combine these because they're on the outside. So we have 4 times the square root of 8. So does 8 have any factors that are perfect squares? We should recognize that the factors of 8 are 1 and 8 and 2 and 4. 4 is a perfect square. So the 4 on the outside times 4 times 2, because those are the factors of 8. This right here is a perfect square. 4 times the square root of 4 is 2. So that 2 comes from the square root of 4. And on the inside, we still have the square root of 2 because it isn't a perfect square. Then again, on the outside, we can combine things. We can multiply things on the outside of the radical together, and our final answer would be 8 square root of 2. Here. The square root of 40 divided by 36. So we can use the quotient property here, the square root of 40 over the square root of 36. Again, slow yourself down. Are either of those numbers a perfect square? Yes, 36 is a perfect square. So one step at a time, simplifying it, the square root of 36 is 6. And we have the square root of 40 on top. So 6 is just a number now. So now we can talk about the numerator. Does 40 have any factors that are perfect squares? So let's write down the factors of 40. 1 and 40, 2 and 20, 4 and 10, 5 and 8. Which factor pair has a factor that is a perfect square? 4 and 10, because 4 is a perfect square. So we can separate the square root of 40 into the square root of 4 times the square root of 10, and that's still all over the value of 6. 4 is a perfect square. When we take the square root of 4 is 2, so that 2 came through with the square root of 4, but we still have the square root of 10 on top and the square root of 6 on the, and the value of 6 on the bottom. Now, double check yourself. Does 10 have any factors that are perfect squares? And if you're not sure, write out the factor pairs. So 1 and 10, 2 and 5. It has no other factor pairs. None of those numbers are perfect squares. So the square root of 10 is simplified and can't go any further. So what we have here is 2 over 6 times the square root of 10. 2 over 6. Can that be simplified? Absolutely. 2 over 6 becomes 1/3. And we still have the square root of 10. And we can clean that up to say that the square root of 10 divided by 3 is the simplified form of the square root of 40 divided by 36. Rationalizing the denominator. To rationalize the denominator, it means that we are eliminating radicals in the denominator. We cannot have things that look like the square root 1 over the square root of 2. That radical is in the denominator, and that means it's not simplified. To rationalize the denominator, we're going to multiply the expression by a fraction equivalent to 1, such that the denominator becomes a perfect square. When we are finding equivalent fractions, so for example, 2/3, if we wanted to find an equivalent fraction, we would multiply that by something that is equivalent to 1. An equivalent fraction to 2/3 is 4/6. And we multiplied this right here by something that was equivalent to 1. It doesn't change its value, it just changed the way that it looks. So we're going to do the same thing when we look at numbers that have a radical in the denominator. So our ultimate goal is that we want to multiply it by something equivalent to 1, so it has to be a fraction, and that our final answer, that this denominator right here, is a perfect square. And actually, I should clarify that it's a perfect square, the square root of a perfect square, because a square root and a perfect square cancel each other out. So we think about what we can do, what we can multiply this to so that this number inside becomes a perfect square. If we multiply this by the square root of 2 over the square root of 2, this right here is equal to 1. Anything divided by itself is equal to 1. And if we remember our rules of multiplying fractions, we can multiply straight across. So 1 times the square root of 2 is the square root of 2. And the square root of 2 times the square root of 2 becomes the square root of 4, because we can multiply things inside radicals together. Now 4 is a perfect square. So we are able, square root of 2 is on top. 2 is not a perfect square, but the square root of 4 becomes 2. So the simplified version of 1 divided by the square root of 2 is equal to the square root of 2 divided by 2. Let's do a harder problem. We're going to rationalize this denominator. We need to multiply this by something that's equivalent to 1. So we know it has to be a fraction. And we want this denominator to be the square root of a perfect square. So the shortcut is to say, well, I'm just going to multiply this fraction by the denominator. So the square root of 5 divided by the square root of 5. But it doesn't matter what you multiply it by, as long as it's equivalent to 1 and you get this to be a perfect square. So on top, 3 times the square root of 5, things inside square roots can be multiplied together. Things outside square roots can be multiplied together, but you can't cross over. So we can't distribute that 3 into the square root. So this stays 3 times the square root of 5. And on the bottom, we can multiply these together because they're both inside a radical. So we get the square root of 25. So on top, we have 3 times the square root of 5. And on the bottom, since 25 is a perfect square, the square root of 25 is 5. And this is the simplified form of 3 divided by the square root of 5. And to check ourselves, we could put that in the calculator and see if the decimal equivalent of this and this are exactly the same. But this is our final answer. Here we have a fraction inside a radical symbol, so we can separate that. The square root of 17 divided by the square root of 20. So we have a square root on the bottom. So we know we have to multiply this by something equivalent to 1, so it has to be a fraction. And our goal is that we have a square root on the denominator that has a perfect square on the inside. So on the last slide, I said the hint would be to multiply it by the square root of 20, because square root of 20 over the square root of 20 is equivalent to 1. But can we multiply it by a different square root value that would also give us a perfect square? So the square root of 5 over the square root of 5, 20 times 5 is 100. 100 is a perfect square. So slow yourselves down and think about factors and how to get to perfect squares. So on top, we have the square root of 17 times the square root of 5. And I could combine those, but I'm not for just the second. And on the bottom, the square root of 20 times the square root of 5 becomes the square root of 100. 100 is that perfect square. So I'm going to move down here so I have room. The square root of 100 is 10. And on top, we have the square root of 17 times the square root of 5. Now, I haven't combined those, the 17 and 5 yet, because sometimes it's easier for us to think about factors that are perfect squares with smaller numbers. So 17, does 17 have any factors that are perfect squares? Well, 17 is a prime number, so its factors are 1 and 17. So no. And does 5 have any factors that are perfect squares? No, because 5 is a prime number, so it's 1 and 5. So neither of those numbers have factors that are perfect squares. So when we multiply these numbers together, we get the square root of 85 over 10. And you could double check yourself, but since 17 doesn't have any factors that are perfect squares and 5 doesn't have any factors that are perfect squares, then 85 is not going to have any factors that are perfect squares. And that's just the rules of multiplication and knowing our factors. So our final answer is the square root of 85 divided by the square root of 10. So the last one, square root of 63 divided by the square root of 8. Use the quotient property to separate those. We have a radical in the denominator, so we know we need to multiply it by something equivalent to 1 so that we can get a perfect square in this radical symbol, because that is the only way to get rid of that square root. So what times 8 will give you a perfect square? The closest one would be, multiplying it by 2 would give us 16. So, and 16 is a perfect square. Now, if you forget, you could multiply it by the square root of 8. And I'll do that down here so you can see the different work. But this gives us a smaller number to work with. On top, we can separate this into the square root of 9 times the square root of 7. 9 is a perfect square. Oops, I'm sorry. Not up top there yet. I was jumping ahead of the game. This has to be the square root of 2, because this right here has to be equal to 1. So on top, we have the square root. As we start to get good at these, we can say, well, instead of multiplying 63 times 2, I can separate that, the square root of 9, the square root of 7, and the square root of 2. 9 and 7 are factors of 63, and we're recognizing that 9 is a perfect square. So we're kind of combining steps here. If that's too much for you, you can do it on its own. So the square root of 9 is 3. Square root of 7 times the square root of 7 times the square root of 2. And on the bottom, since 16 is also a perfect square, we get 4. So does 7 have any factors that are perfect squares? No, because 7 is a prime number. Does 2 have any factors that are perfect squares? No, because 2 is a prime number. So we can combine those, and our final answer is 3 times the square root of 14, all divided by 4. This is the most simplified version. Now, let's do this again, but let's do it with multiplying this by the square root of 8. Because we could do it that way too. On the bottom, we end up with the square root of 64. That's our perfect square. And on top, we end up with the square root of 9 times the square root of 7 times the square root of 8. We know that the square root of 9 is going to be 3. The square root of 7, we know that 7 doesn't have factors that are perfect squares, but 8 does. So the square root of 8 can be separated into the square root of 4 times the square root of 2. So we have 3 from the square root of 9 times 2 from the square root of 4. Square root of 7 times the square root of 2, all divided by 8. 3 times 2 is 6. Above we talked about square root of 7, square root of 2. Neither of them have factors that are perfect squares. So it's going to be square root of 14. And the bottom we have 8. We have to stop ourselves and say, oh, we have to simplify that fraction. So the simplified fraction, 6 over 8, is 3 over 4 times the square root of 14. And we end up with the same answer, but a lot more steps. So either method is fine and either path is fine. You just have to make sure that you are getting to the end to get that very simplified version.